Okay, starting chapter 3, 3.1, and this is just titled Functions. It's going to be an introduction to functions. Lots of vocab in this one. Starts out where it's a little bit, can be tricky to understand, but once you get it and see the assignment and look at the application of it, it's not bad at all. So you got to bear with me here because there's a lot of vocab. First one is a relation. And what a relation does is pairs inputs with, that little C, remember, with a line over it is with, outputs. So I'm going to have some inputs and I'm going to have some outputs. What a relation does is pairs those together. It shows that there's a relationship between them. A function is a relation. So we should be thinking right now, hey, a function is going to have inputs and outputs, and it certainly does. A function is a relation that pairs each input with exactly one output. A function is a relation that pairs each input with exactly one output. There's a handful of ways here we can describe functions, and we're going to look at each of those. Functions can be described as the following. We will see functions represented by equations. You're going to be given equations and asked, is it a function? You're going to see data presented in input, output tables. There are going to be word problems. You're going to be able to look at a graph and tell me whether that graph is a function or not, if every input has exactly one output. And you'll see functions represented as ordered pairs. Remember, ordered pairs are x, y. And if I have an x and a y and I have an xy coordinate plane, I will plot those as an ordered pair as a point in that plane. Main thing we're going to do when we plug through these is we're going to determine, is the relation, is the pairing of the inputs and the outputs a function? Do those pairings of inputs and outputs, does every input have exactly one output? If it does, that's what's going to make it a function. Here's what this looks like. We'll call this letter A. There's going to be a few of these. Here I've got some ordered pairs. -2, 2. -1, 2. 0, 2. 1, 0. 2, 0. So here I have these 1, 2, 3, 4, 5 ordered pairs, and we want to know, is this relation a function? Are these inputs and outputs, is it representing a function? Does every input have exactly one output? Remember, we have an x and a y. This x, this is what we call our input. The y in the ordered pair is what we call the output. So we need to look at these inputs and see if every input, every X value in these ordered pairs, if they have exactly one output. When I'm given a list of ordered pairs, like it says, I am going to look at those inputs. And here I can see every input, every X has exactly one output, meaning this does not repeat. -2 has a Y of 2. -2 doesn't have a Y of 2. And also -2, I don't see -2 listed as an input here. So if I added the point -2, now I have two inputs that are going to different outputs. In order to be a function, these inputs or these X's have to have exactly one output. And we're going to do plenty of these. So when I look at my X's here, my inputs do not repeat. So is the relation a function? Yes. And the reason, your explanation should be every input, every X value has exactly one output. My Y's. I don't have any of my inputs that are repeating, so they all have one output. I wouldn't write the same point if I had the same ordered pair here. You wouldn't write it twice. I know that I have two inputs, but they're going to the same output. They have the same. If I change that -1 to a 4, now this is not a function because -1 has outputs of 2 and 4. Look at your X's. Your Q is going to be if those X or those inputs repeat. Let's look at letter B. Here's 4, 0, 8, 7, 6, 4, 4, 3, 5, 2. And the question still is the same. Is the relation a function? And again, look at your inputs, your X's. I'm just going to lightly circle them. I'm going to do a little comparison here. I have 4, 8, 6, 4. I have inputs that are the same. I have 5, 2 as well. What's keying me in is these 4s. Each input does not have one output. My input of 4 has an output of 0. My input of 4 also has an output of 3. That makes it not a function. These have to be paired. One input, one output. My output right here, my Y. If my X is the same and my Y's are different, it's not a function. Every input does not have one output. In this case, I would say no. And the reason or the explanation, 4 has 2 outputs. And I'm just going to list them here. It has 0 and 3. Every input does not have one output. It's not a function. I'm going to do something that's called mapping. And you will see data presented this way. It's kind of an input-output table. But what mapping does is it makes ordered pairs. And it's another way of looking at something to see if it's a function. So here's my input, again, which is my X. Here's my output, which is my Y. And I'm just going to make a little list here of what my inputs are, or my X's. I have inputs or X's of 4, 8, 6. Now I have 4 again here. Do not write that 4 again. I've already got it there. If I write this 4 again, mapping isn't going to really tell me that much about it if I'm not paying close attention. Write it once. The same thing holds true with your outputs. If one of these outputs repeat, we only write it one time. So I have 4, 8, 6. There's 4 again. I'm not going to write it. And I have 5. I have outputs of 0, 7, 4, 3, and 2. And what this mapping is going to do is pair my inputs with my outputs, just like the ordered pairs up here. 4 is paired with 0. 8 is paired with 7. 6 is paired with 4. 4 then is paired with 3. 5 is paired with 2. And I can see right here, back to my definition of a function. Each input has exactly one output. If I look at my x's here, this little branch coming off this tree trunk has 2 branches. This input of 4, this x of 4 has an output of 0 and has an output of 3. You can definitely draw a map to help you see it. Remember, you only write the values one time if it repeats, because you can see if I would have wrote a 4 here and then took that 4 to that 3, each one of these branches would just have 1 coming off of it. But 4, you would have to pick up on the fact that you wrote 4 twice. Just write it once. Look for this double branch coming off there. It could be a triple branch. I could have an X that has 3 different outputs. Mapping can help us see that. You will also see input-output tables just written horizontally. Input, which is your X, output with your Y, and this is just another way of representing data, representing the XY ordered pairs. I'm going to say I have X's of 2, -1, 0, 5, whoops, not 5, 0 again, 1, and 7. Inputs are X's of -2, -1, 0, 0, 1, and 7, -3, 4, 5, 6, 7, 8. And hopefully you're looking right now and the question remains the same, is the relation a function? Hopefully you're recognizing, no, this is not a function. 0 repeats, my input repeats. And for 0, I have an output of 5 and an output of 6. This is not a function. Why is it not a function? 0 has 2 outputs. And in order to be a function, every input has to have 1 output. 0 has an output of 5 and 6, makes it not a function. And I'm just going to write 5 and 6 there. Has 2 outputs of 5 and 6. If I made a little map, which I will do so we can get, you can see the relation between a chart. And remember, these are XY ordered pairs. I could plot these. This is the ordered pair 2, -3, -1, 4, 0, 5. You get what I'm doing here. I could keep writing these as ordered pairs. I'm lazy, I'm not going to do that. But this is what we have here, and we have input outputs over here. What are my inputs? 2, -1, 0. I don't write the 0 twice. 1 and 7. My outputs are -3, 4, 5, 6, 7, and 8. And now I just map these out. I have the ordered pair 2, -3, -1, 4. I have 0, 5, and I have 0, 6. And I can see right here, this input has 2 outputs. It's not a function. And that's how mapping can help us see that. I'll map a couple more before we're done too. Let's look at this one. call this D. I'll take 2, -3, -1, whoops. Let's go -1, 4, 0, 6, and 1, 6. Again, the question is the same. Is the relation a function? You could certainly look at your inputs. My inputs don't repeat. It's probably going to be a function. It is a function. I'm going to do a little input-output table. The last time I'll probably map. Maybe one more. 2, -1, 0, +1. My outputs are -3, 4, 6, and I've got 6 again and I don't have to write it. 2 is paired with -3. I have the ordered pair -1, 4. I have the ordered pair 0, 6, and I have the ordered pair 1, 6. And I can see by mapping this, just because both of these go to one output, doesn't change the fact that this is a function, because each input has one output. I can have an input that goes to the same output. Remember, the definition is every input has exactly one output. I can't have an input that gives me 2 different outputs. This is a function. And why? Because every input has an output. Exactly one output, not just a output. Exactly one. Here's letter E. Got the ordered pair -1, 6, 2, 6, 3, 6, and 4, 6. And again, look at your inputs. They're all different. Doesn't matter that the output is the same, because if I map this in an input-output table, you will see -1, 2, 3, and 6. Yes, they all have an output of 6, but every input has exactly one output. Doesn't matter that they all go to 6. This is a function. Why is it a function? Because every input has exactly one output. We can also look at these graphically. And we need a definition of something here. This is called the vertical line test. It's a really handy tool, and it should tie everything together on the definition of a function. Definition of a vertical line test: a graph. So I've got a graph. That graph represents a function, meaning I'm going to give you a graph and ask you, is this a function? A graph represents a function when no vertical line passes through more than one point on the graph. A graph is going to pass a vertical line test if I run a vertical line, an infinite number of vertical lines through the graph, and it only hits the graph in one point. If it hits the graph in 2 points, it's not going to be a function. I'm just going to make this a little first quadrant coordinate plane. Here's my x-axis, here's my y. I'm just looking at quadrant 1 of a coordinate plane. I don't have anything here, here, here. I'm just looking at this graph. And if I have something that looks like this, Here's a set of data, and you're going to be asked the same question. Is it a function? I will tell you, yes, this is a function, and the reason it is because it passes the vertical line test. Passes the vertical line test. When I draw vertical lines through these data points, it hits the graph in exactly one spot. It can only cross these data points one time. It passes the vertical line test. I'm going to label this one 1, 2, and 3 on my y-axis. Here's my x-axis. I will go 1, 2, and 3 on my y. And I'm going to give you this graph. Question is the relation a function? Is this graph representing a function? Vertical lines that hit the graph. One spot, but look what happens here. It crosses both of those points there. It hits the graph in more than one spot. It hits here and it hits here. This is not a function. Why isn't it a function? Because it does not pass. It does not pass the vertical line test. When I draw this vertical line right here, it hits the graph in not one, but 2 points. When that happens, it's not a function. And if I think about it, it kind of makes sense because this ordered pair right here is 3, 1. This ordered pair is x is 3, y is 2. And if I notice, based on what we did up here, looking at this data, my inputs are the same. 3 has an output of 1 and it has an output of 2. And in order to be a function, every input must have one output, exactly one output. In this case, 3 has an output of 1 and 2. It's not a function, and that's why graphs like that will not pass the vertical line test. One more to look at here. Here's my x and my y, another first quadrant coordinate plane. Both my x and my y are positive. I will call this 1, 2, 3. And this time on the x, though, I'm just going to go 1 and 2. And I'm going to give you a graph that looks like this and ask, is this relation a function? And I hope that you can see right away. Now, these lines are connected. Right? These dots, there's an infinite number of points that make up this graph versus this one. I only had to draw 1, 2, 3, 4 vertical lines. This one, I can draw an infinite number of lines because this data is continuous. And I can see it doesn't matter how many lines I draw, it's always going to hit the graph in 2 spots. And in 2 spots. Let's say this is the ordered pair. It's a little bit off, but I'm going to call this. I can make that graph go through there. My vertical lines are still here, still hitting the graph in 2 points. But again, to prove our point, this is the ordered pair 2, 1. This is the ordered pair 2, 3. And again, I can see that the input of 2 has an output of 3 and 1, and that's why this vertical line hits it in 2 spots. Goes through those points right there. This is not a function. Why isn't it a function? Because it doesn't pass the vertical line test. No, the relation is not a function, and I'm just going to say does not pass the vertical line test. And hopefully that's starting to come together now, why that would work. Why the vertical line test is a nice test looking at a graph. It's going to tell me if I have x's that are the same. Next thing we need to look at is domain and range of a function. The domain and range, and hopefully you've heard of this before, doing in-person classes this week. Some had, some hadn't, more hadn't or didn't remember what domain and range were. We're going to do some definitions. The domain of a function is the set of all possible input values. And remember, input are my x's. We're just building our vocabulary of different ways to call x. I can call x the domain. Those are the possible values of x. We call x input, and we call x just x when I'm talking about a coordinate plane. Input, x, domain. Domain refers to x. Input refers to x. Hopefully you're picking up that if I say the range, well, that's going to be my y's. It's going to be my outputs. The range of a function is the set of all possible output values. And remember, those are my y's. Range, output, y. So we've had input, x, output, y, and now we've just associated domain with possible x values and range with possible y values. Draw a little box here. Taking you back to 3rd grade doesn't have to be a fancy box, but I'm going to make a little function box. And some students that were in person did remember making a little function box. We put something in, we get something out. Functions are everywhere. They're in your electronics. They're in the light switch. If I go to turn on the lights in my room here at school, I am definitely hoping that when I turn on the lights, I expect the one row of lights to come on. I don't expect the basketball hoops to lower in the gym, my car to start, and my projector to turn on by flipping the light switch. I expect one thing to happen: the lights to turn on. Why do they turn on? Because it's wired that way. That other stuff isn't wired up, whether digitally or hardwired. Every input has one output. It's a little function box, they call this. What I have over here is stuff coming in. You have inputs. These are where my x's go, my inputs and my x's. It's where your domain is found on the input and the x side. And we also call this the independent variable. X is my independent variable. I can get stuff out of this. If I have an input, what I get out is an output. What I get out is a Y value. What I get out is a range associated with that domain. And Y is also my dependent variable. The value of Y, my range, is going to depend on the value of X. Because what goes in this function box is an equation. We'll take this one. Y is equal to negative 3x. Y is equal to negative 3x. Let's say I have an input or an X value of 2. I take that input, that X value, the domain, the independent variable, and I plug it in. Y is equal to negative 3 times negative 2. Well, what's negative 3 times negative 2? Positive 6. With this function, if I have an input of negative 2, I have an output of 6. With this function, I have an ordered pair of negative 2, 6. This is the introduction to kind of linear equations here too. If I graph this, this is a line. And what I know now is that the ordered pair, negative 2, 6, lies on that line. This point makes it up. It's part of the line. And I could keep plugging it in. If I have an input of 1, well, negative 3 times 1, I would have negative 3. That's a point that lies on the line. And you could keep going. This is how we use the function. Y is your dependent variable. My value of Y right here depends on the value of X. If X is negative 2, Y is 6. But I got a value here of negative 3. This value of negative 3 depended on what I substitute in for X. Y is your dependent variable. Let's say I had this equation. Y equals 50x plus 100. Let's say this models a plumber coming over to your house to fix your drain. He charges $100 for a house call and then maybe $50 an hour to do the work. Your cost, the Y, is going to be dependent on, Y depends on the number of hours that the plumber's there. If he comes over to your house, let's say he's super nice and there's just a toy or something stuck in the drain your little brother or sister put down there and just pulls it out. It's like, I'm not going to charge you. I work 0 hours. You're still going to pay $100. Let's say he had to take it apart. He had to take it apart and he spent 1 hour doing it. It'd be 50 times 1, which is 50 plus 100. My cost would be 150. When the plumber spends 1 hour, it's 150. If he spends 2 hours, well, 50 times 2 is 100 plus 100 is 200. My cost, my Y, depends on the number of hours he works. Dependent is Y, independent is X. You are going to use this to describe domain and range. Describe domain and range. And again, this is one of those things that can be tricky at first, but it's really not. I'm going to make a coordinate plane now that is, I'm going to try to be as accurate as possible as far as labeling my axes and getting some points on there. I'm going to bust this X up into 1, 2, and 3, trying to make it as even as possible. I will do the same on the negative side of x to the left of the origin. Make this a little bit bigger here because I'm going to go up 3 on the y, and then I'm going to go down 3 as well, -1, -2, -3. There's a little coordinate plane. Now I've got my 4 quadrants, quadrant 1, 2, 3, and 4. And I'm going to give you these points here. And I am going to ask you to describe the domain and the range. Notice I have individual points of data. This isn't a line connecting them. I can't just connect that. Domain, definition, is the set of all possible input or x values. I need to find out what my x's are. I have 1, 2, 3, 4 points. I should expect 4 domain values. 1, 2, 3, 4. You have 4 points. I would expect 4 range values. None of them are going to be the same because they're not lining up with each other. It always helped me to circle these, and I would encourage you to do the same. On the test or quiz, I always put an outlier point somewhere, maybe at the origin, maybe down and around. People go quick and they'll always miss one. Circle them. Then you can even make it easier and just label them. This is the ordered pair -3, -2. This is -1, 0. This is the ordered pair 1, 2. This is the ordered pair 2, 3. Your domain is your x's. Just write them. Got -3 as a value of x as an input. I've got -1. I've got +1, and I've got 2. For my range, I look at my y's. I've got -2. I have 0. I have 2, and I have 3. My values of y. Domain x, range y, input, output. That is when you have what we call discrete data. These are not connected. These are individuals stand on their own points. Versus something that looks like this. And I'm going to make another somewhat accurate, as close to accurate as possible, coordinate plane. Got an x, got a y-axis. I will again try to split this up evenly as possible, going by 1s out to 3 in both directions. -3 here to the left. I will go up to 3 on my y in the positive direction, and I will go down to -3 on the y right there. So here we go. Got this coordinate plane by 3s. I'm going to put a point there, a closed circle. And I'm going to make this graph right here. And hopefully you're noticing, this graph is different than this one right up here. This is what we call continuous. These points that lie on this graph are all connected. There's an infinite number of points that lie in this line. And remember, to find domain and range, we need the set of all possibles. There's an infinite number of points, an infinite number of x and y values that lie on this line. This is a function because it passes the vertical line test. And now you are asked to describe the domain and range. Domain and range. Domain is your X. Range is your Y. I would start by doing it like that. Because we need to include every X and every Y in here, we need to make an inequality. We need to give it an interval. Isn't it true that my X's are between -2 and +3? Here's my values of X's. They range between -2 and -3. And remember, there's an infinite number of points on here. This is a closed circle, so I need to include -2 in it. So you are going to need an inequality that is an and statement that is less than or equal to, and it is going from -2 to +3. And hopefully that's making sense when you look at it. Possible values for X, the possible set, well, it could be anything that's between -2 and 3. That will give me every possible value of X. That is my domain. The corresponding range, you are going to have to look at your Y's. And again, I can see I am going between +2 and -2. -2 to +2 is going to include all my Y's. That's a closed circle. That's a closed circle, so it's going to be less than or equal to, low number goes on the left. It's running between -2 and +2. You're concerned with Y's that are between -2 and +2. And we write this in interval because you could write an infinite number of points that lie on this continuous data. If I changed those circles to open circles, my interval would be the same. What would change is my sign. You would have something that -2 is less than X is less than 3, open circle. That would be your domain. Your range would be -2 is less than Y is less than 2. I just wouldn't include the equal if those were open circles. Lots of stuff in there, but the homework is not tricky. Give it a whirl.